Okay, very good. We have Paolo Pichini that will tell us about Compton scattering and Kerr black holes. Please.
So thanks a lot for the invitation. And so what I'll be talking about today is a work I did with my supervisor, Henrik Jansson, and our collaborator, Marco Chiederoli, which fits into the story of describing binary black hole systems and gravitational waves using QFT amplitudes. So I should thank Carlo because he basically introduced the topic for me, so I have less work to do. So in this case, I will focus on spin and spinning black holes. So we're going to start this by this paper by Justin Vines in 2017 that wrote down the Kerr linearized energy momentum tensor in this particularly nice exponential form, which you can obtain by contracting it with an on-shell graviton polarization. And round about the same year, a paper came out by Nimar Ahmed, Huang and Huang, that basically just presented these particularly nice looking amplitudes between two massive higher spin states and a graviton within the context of the so-called massive spinor-helicity formalism, which is essentially given by these brackets that are, you should think of them as just some spinor products between some definite chirality Weyl spinors. So I mean, at this point, this was written just because well, not just because it looks nice, but it was nice from the point of view of QFT. There was not really any reason to expect the two things to be related. But a year later, some other papers came out that showed that this can be rewritten in the following form. So I think all of you can probably see the resemblance. And so it was understood that you can match Kerr energy momentum tensors using these special amplitudes if you identify the spin variables of your black hole with some sort of an expectation value of a Lorentz generator, essentially, so your angular momentum charge with the polarization states of your black hole. And also for any fixed spin S, this exponential truncates to the power 2s of your like spin. So in order to get the full Kerr, you need to take a spin to infinity limit of your quantum field theory. Okay, so this was the premise. And what we try to do in our paper is understand a bit more, like, why are these amplitudes special? Where do they come from? What makes them special from the point of view of a QFT? And what we did is that we dig up some higher spin papers, and we find that there's a known constraint on the Feynman rules of higher spin theory, which I will refer to as a current constraint. So what this says is that if you take a 3-point vertex between two massive spinous particles and a graviton, or a photon for that matter, and you contract it with the momentum of this leg, so this should be an off-shell leg, then you should get something that vanishes in the massless limit. So in other words, when you take the mass to 0, you recover gauge word identity for gauge invariance on that leg. And this was used in 1992, for instance, to show that the G equals to 2 is the universal 3-level value for the geomagnetic ratio of elementary particles. So what we find is that it can tell us more, and in particular, it's able to fix uniquely the amplitudes I just showed you before up to the value of spin 5/2. And for any spin higher than that, those amplitudes appear as the solution. It's just not unique anymore. So there's more that one should think about that. But because also this leg is an off-shell leg, this actually says more than just a 3-point amplitude information. And we're able to use it to partially fix the 4-point contact terms of the Compton amplitude, so this guy up here, which are needed for an next to leading order computation in actual gravitational wave calculations. And okay, so if you assume some other physically motivated assumptions that I don't have time to go into right now, you can actually fix these contact terms uniquely, and we've done so up to spin to the 5/2 gravity. So one caveat I should say is that this new result we have for the Compton, this is that I've given you is not a proof that this will match Kerr. At the end of the day, you still have to check explicitly, for instance, from black hole perturbation theory, which was discussed before today. But yeah, we're presenting this nice framework where you can understand these results. And okay, so I just want to flash quickly what we find. So this is the case of spin 5 gravity. So there's a non-minimal term. The story is actually very similar for a spin 3½ massive particle coupled to the photon. So you can see there's this nice correspondence that I would say is not yet fully understood of the non-minimal term. And yeah, okay, we present the amplitudes written in spinor form. If you want to know more about them, you can ask at the poster session. So just to summarize what I've been talking about, we have this special class of higher spin amplitudes that match Kerr black hole observables, and we are beginning to understand where they might come from. And in particular, they come from these special high energy properties within higher spin quantum field theory. And also, there's hope that we are able to push to NLO because this current constraint goes beyond 3 points, and so we're able to fix the 4-point amplitudes as well. And the obvious directions, well, one of them is an explicit check against Kerr observables via, for instance, black hole perturbation theory. There is also a question of what happens beyond spin 5². I mean, we need to take spin to infinity, but higher spin theory is hard. So hopefully there is more that we can understand beyond this constraint that would give us a complete understanding of what Kerr means from an amplitude viewpoint. And yeah, okay, finally, it might be interesting to compare to other known theories of higher spin that we have. Like string theory is the obvious example, and maybe we can learn something from that. So thank you very much, and I'll take any questions.
Thank you very much. So do you have any questions? So is there a reason to expect that? So you described two seemingly different objects that manage to be related in some way. I mean, is there a deeper understanding of why is that, or it's just like as we saw, yes, as we saw today, maybe some something that is suggestive, but still don't know.
Sure. Let me go back to
for the first slide.
Yeah. So yeah, this one here. I mean. Yeah, so why are Kerr black holes in any way related to fundamental particles? Yeah, that's the question. I mean, I can't, there's no complete understanding of why it's the case. My intuitive understanding is that, so, I mean, what distinguishes fundamental particles from composite particles, for instance, is that they don't have an inner structure, right? I mean, this is what fixed, I don't know what I did, but so you wouldn't need G equals to 2 for a composite particle, for instance. This is a feature of really fundamental objects that don't have an inner structure. And in some sense, Kerr black holes are like that. So, as opposed to a neutron star that can have an equation of state with complicated stuff happening inside that will like influence its gravitational properties. A Kerr black hole is, by the no-hair theorem, uniquely fixed by its mass, spin, and charge. And in that sense, is really similar to the properties of a fundamental particle. So that's what I can say. But yeah, I mean, there's more to be understood, I think, for sure.
Yeah, it could seem that you're checking, like you need a specific theory, right? Specific couplings or.
Yeah, absolutely. And I mean, for low values of spin, like up to spin equals to 2, these specific theories are the standard quantum field theories you know and love, like, I don't know, minimally coupled electrons or W bosons, or these theories, because they are the fundamental theories of spinning particles. So yeah, hope that answers the question.
Yes. Any other observations or questions? So if not, we can thank again.